This video explains the Clausius-Clapeyron equation. Earlier in this chapter, we've been looking at phase diagrams, which are just maps that tell us the stability of the various phases of a substance as a function of conditions of pressure and temperature. These phase diagrams are characterized by the phase boundaries, which are these lines that separate the various phases. Right, so what we've been doing as of late is to try to see if we can quantify aspects of these phase boundaries. And what we actually learned how to do the other day was to measure or determine what the slope of any one of these lines is from the Clapeyron equation. Okay? And the result was this. The slope of the phase boundary, the phase diagram, is simply the change in enthalpy for the phase transition divided over the temperature at which you want to calculate that phase boundary, and the change in molar volume in the phase transition from alpha to beta. Right, this Clapeyron equation applies to all three phase boundaries, but it requires you to know quite a bit of information about those phase boundaries, including what the molar volumes are for the phases involved at the conditions that you're interested in. It turns out that you can make one simplification to this term when you consider phase transitions that involve the gas phase. So the Clausius-Clapeyron equation, which we're going to derive from the Clapeyron equation, is only going to apply for transitions, phase transitions or equilibria between the liquid and the gas and the solid and the gas. Okay? It will not apply to the solid and the liquid phase transition. Right, so what is the approximation involved here? Well, the first thing that we're going to do is assume that the final phase of the phase transition is the gas phase. Okay, so we can rewrite that expression by simply writing that this is going to be alpha to gas and beta to gas. Okay, that's why this approximation, this Clausius-Clapeyron equation, only applies to the liquid to gas or solid to gas phase boundaries. Then we can examine what happens to the change in molar volume in the denominator once we have that the final phase is the gas. Right, so delta Vm, when you go from solid or liquid to the gas, is going to be identical to the molar volume of the final phase, which is the gas, minus the molar volume of the initial phase, which is either the liquid or the solid. Right, so this is an interesting comparison, because we know that the molar volume of a gas is generally much greater than the molar volume of a liquid or a solid. For example, for water under ambient conditions, the molar volume of the liquid phase will be about 18 mils or so. The solid phase will be about 19 mils, milliliters. But when you go to the gas, under the same conditions, the molar volume will be about 24 liters. Okay, so there's about 1,000 times greater molar volume for the gas than the liquid or the solid. Because this number then is again, for water and for other substances, is much greater than that. A good approximation is to actually neglect this molar volume with respect to the molar volume of the gas. So we're going to say that this is equal to the molar volume of the gas. Okay, so that is one simplification that makes things a little easier. The other thing that we can do is say, well, what is the molar volume of a gas? Well, if we're working under conditions of temperature and pressure in which the ideal gas approximation can be used, and this is generally true when the pressure is not very high, we know that the molar volume is just equal to the volume occupied by 1 mole of the substance. Here we can apply the ideal gas equation of state and make this identical to RT over P. Okay, that comes directly from the ideal gas equation of state. And then what that means is that we can actually then retake the Clausius-Clapeyron equation and rewrite it like this: differential of P, differential of T. This is the Clapeyron equation. Okay, delta H molar from alpha to the gas, and then we have here the temperature, and the approximation is that we can substitute this change in the molar volume just by the molar volume of the gas, but we agree that this is equal to RT over P. So this is going to be RT over P. Alright, this is just going to end up being pressure times the change in molar enthalpy of the phase transition that finishes in a gas, and then over RT squared. Okay, and this is what we call the Clausius-Clapeyron equation, the slope of the phase boundary in the phase diagram that lead to a gas, okay, is equal to this simpler expression. Notice that this is much simpler than that, because you're usually asked to calculate the slope at a particular point in the phase diagram, in the phase boundary, right? That point has to be determined by the pressure and temperature. So these two numbers are already a must in the statement. Then the other other variables that you have is the R constant, and then the enthalpy of the phase transition, which is also known. So again, usually all of these numbers are actually known, and that means that it's fairly easy to calculate what the slope of the phase boundary is. Again, when you use the Clapeyron equation, you need to know the molar volumes, which are usually not available, or they're more difficult to find when you have solids and liquids. Okay, so this is the Clausius-Clapeyron equation, and it serves to calculate the slope of the phase boundary for the liquid to gas or solid to gas lines in the phase diagram.